So I expect that you know how to do stoichiometry at this point, that you can go from moles to moles, grams to moles to moles to grams, do all of those conversions. We're going to take that and we're going to apply that to this new thing called theoretical yield. Now the theoretical yield is basically what you've been doing. The stoichiometry you've been doing is calculating the maximum amount of product that can be produced. You're calculating, all your calculations that you've done up to this point are theoretical. They are assuming a perfect world. These are the ratios that things should react in. But it's not necessarily as perfect as our calculations come out to be in the real world. So that's where percent yield comes in. So the amount calculated using your stoichiometry methods is the theoretical yield. That's the maximum amount of product that can be made given the amount that you start with. Now the actual yield is if you actually go into lab, run the experiment, start with the amount you expected, how much product actually comes out. This is taken from experimental results or lab results, or it'll be given. If it's given in a problem, it'll say, okay, this is how much actually came out. Now the equation for this is actual yield divided by theoretical yield times 100 gives you percent yield. So just to give you some context, or a little bit, or an easier example, maybe that's easier to wrap your mind around. Let's say that a farmer is planting the fields and they expect their yield to be 200 bushels per acre. So that's a measure of how much corn comes off the field. And let's say that they only get 180 bushels per acre. We would say that they had a 90% yield from what they expected, right? They got 90% of the amount that they expected to get. So that would be an example of like percent yield in terms of farming. In terms of chemistry, it's the same concept. How much do you expect to get? How much did you actually get? And then what percentage is that? Sorry, I forgot to put the times 100 in there. But that would be kind of maybe an easier example to understand before we get started here. Otherwise, the shortened version of this is AY over TY, actual yield over theoretical yield, is how you'll see it. So it says calculate the percent yield of sodium chloride when 130 grams of sodium reacts with chlorine to give 63 grams of sodium chloride. So one of the trickiest parts of these problems is understanding which number do I start with, 130 grams or 63 grams. So what it's saying is 130 grams of this, let's erase that, 130 grams of this is going in, excuse me, and then it says 63 grams of this is coming out. So this is the amount that's actually coming out. This is the amount that we're putting in. Based on this number, how much should we expect to get out? Because it's telling us 63 grams is actually coming out. So here's how we set this up. Well, first we've got to balance it as always. So we balance it. I'm going to save a little bit of time by putting 2's in those spots. Now the next step is to set up a ladder. Now the 63 grams is the actual yield. So I'm going to take that and put it down in the actual yield. I save it for later. So we'll just move that 63 down there for now. Now I take the 130. The 130 is what I actually start my ladder with. So if I got 130 grams of sodium going in, how many grams of sodium chloride should come out? So we're going to solve this ladder to figure out how much should theoretically come out. And now, as always, you put your units in, grams to moles, then we go moles to moles, then moles to grams. So you lay out all your units. From here, remember if mole is with grams. If mole is with grams, it automatically gets a 1. Then we put in the molar masses. So you've got the molar mass of sodium down here, the molar mass of sodium chloride up here. For the mole ratios, when it's mole above mole, that's where we go up here. So we take the 2's and we put them in. So now at this point, 130 divided by this times 2 divided by 2 times 58.44, and that equals this number. Now, because we only got 2 sig figs here, we should round it to 2 sig figs, and that's our theoretical yield. So we'll drop that in to our theoretical as 2 sig figs. So now what this means, if 130 grams of this goes in, so let's kind of work this here. If 130 grams goes in, I should expect to get out 330 grams of this. In a perfect world, if this reaction goes to completion, all of this reacts, and I have more than enough of this, then I should get 330 grams. In this case, I only got 63 grams, so that's way less than expected. So this is not a very good percent yield. So if I do the calculations, it ends up being about 19% yield, which I need to round this again. I got 2 sig figs and 2 sig figs. So this rounds to 19%. So based on the amount I actually got out, I got out 19% of what I expected in a perfect world. So in a perfect world, 333 grams, I only got 19% of that. So that is my final answer. I got a 19% yield of sodium chloride. So here's another one. Methanol, which can be produced through the following reaction of CO, carbon monoxide, and hydrogen. If I use that reaction, which I should probably balance first, I check here, I've got 1 carbon, 1 carbon, 1 oxygen, 1 oxygen, but I've got 4 hydrogens, so I should double this. Now I think it's good to go. It says if 190 grams of this, so I've got 190 grams of this going in, it produces 68.4 grams of this. So that's how much it actually produced. What is the percent yield of methanol? So I'm going to set up my ladder. Now my actual yield, I already know that. It tells me it reacts to produce this much, 68.4. So I'm going to take where the actual yield was and put 68.4 grams. Now the theoretical yield, we'll leave that blank because that'll be what we calculate here. Now it says 190 grams is going in, so that's where I start my ladder. 190 grams of CO. So I'm just going to take grams of CO, bring it down, moles of CO. Sorry, I don't know why, my MacBook, I think it just gets slow here, and when I draw in circles, it makes them very jagged. It's really bothering me. So I'll just have to draw a little bit slower, I think. So I bring moles of CO down, I go moles CH3 OH, then I bring moles CH3 OH, and then I gotta go grams CH3 OH. Mole gets the 1, mole gets the 1. I've got a 1 here and a 1 here because it's a 1-to-1 mole ratio. And then how many grams are in 1 mole of CO and how many grams are in 1 mole of this? I'm actually going to pause the video, solve these, and then I'll write them in to save you some time. So I added up the molar masses. This ends up being 28.01 grams per mole by adding up carbon and oxygen. And then if you do this one, it ends up being 32.04 grams per mole. So now at this point I need to do a little bit of math. I need to take my calculator and go 190. I'm going to divide by 28.01. I don't really care about all those ones, so then I'm just going to multiply by 32.04. What I end up getting is 217.34 grams CH3 OH. Gosh, this computer is god-awful slow at keeping up with my writing here. I promise my writing isn't this bad. Now, this has 2 sig figs, so I'm going to round this to 220. Okay, oh, actually, sorry, I took a shortcut there. That's 4 sig figs. I got 4 sig figs, 3 sig figs, so I need to actually go, let's fix this. Make sure we get it right. Okay, let's get the pen back. So we cut it off. It should be 217.3 grams. And at this point, I need to do a little bit of division. 68.4 divided by 217.3 times 100. And it is 31.5. I've got to go to 3 sig figs. 31.5% is my yield. So what this means is I expected to get this much when I did the reaction. I only got this much, or I expected to get this much. When I actually did the reaction, let's say I went out and did it, I only got this much. So 68 is only 31.5% of the the theoretical amount that I should have gotten out of this reaction. So that is how you do percent yield.